Hello, Morgan.
Good morning.
Morning. How are you?
Not bad. Just getting started here.
Yeah.
Pre-coffee.
All right. That's good. So welcome to the meeting. Some interesting things for today. So in the last week, we had one meeting. We had the DevaWorm meeting. And I think Morgan was there too. We covered some papers on, I'm trying to remember what the first paper was, but the second paper was on these wasp's nest and how they're self-organized, and a mathematical model to describe that. So it was pretty good stuff that we covered. I remember having to go through a lot of species names that I wasn't familiar with. So, I know what the paper was. It was the cellular, it was like a cellular zoo type paper where they characterized a bunch of single cell organisms. And they were looking at the structure of the single cell organisms and how they moved, and describing that movement in terms of how it's produced. So it was a pretty good paper. And yeah, so check that out on our YouTube channel for DevaWorm if you're interested. This week I also completed the videos for the active symposium, so that's next week. That's Wednesday through Friday, and you can either register at the website. I think I brought that link up last week, or you can just catch their live stream on YouTube, which is at their Active Inference channel on YouTube. So in some laboratory news, as I said before, these are the new videos that we have up for the Active Inference Symposium. It's not showing the other one, but this is the screenshot. So we have the neurosimulation of spatial intelligence, interdisciplinary underpinnings, and that's a nice overview of spatial cognition and the different ways it's produced, going over some of the details of ecological psychology and spatial cognition, which is a different view than the typical grid cell, place cell view. And then talking about things like path integration and other types of mechanisms for spatial intelligence and single cells, et cetera, et cetera. So, and then it talks a little bit more about how we might produce spatial cognition agents, and it's a nice talk. And then I have this other one on open source sustainability, kind of an overview of the project. As we talked about last week, Sarah did an overview of the project at the GSOC Mentor Summer, so I'm going to do an hour-long version at the Active Symposium. So those are available on our YouTube channel, and then they'll also be featured in the symposium. And then another piece of news, Ankit Grover, this is from LinkedIn. He's starting a new position as student researcher for machine learning for adversarial threat detection at Google. So it looks like he's coming along in his career.
Cool.
Yeah. Did you want to say something, Morgan?
No, I was just saying that's awesome.
Oh, okay.
Yeah, I mean, great job.
Yeah. All right, so that's laboratory news. Actually, I wanted to pull this up. This is Josh Bongard, the talk. I think it was Morgan who posted this in the Slack. This is Ecolopto, and they're introducing Josh Bongard here. So this is just one of his computational granular metamaterials talks called The Tip in the Iceberg, Why Embodiment Matters. So you can check that out on that YouTube channel. And then a few other things from following up from last time. This is Kelsey Hightower. I think this is from Blue Sky. And he says Kubernetes is a sum of all shell scripts and practices system administrators cobbled together over time and presented as a single system behind a declarative set of APIs. Now, we were talking last week about shell scripts and how shell scripting is designed to sort of cut through some of that complexity. And this is kind of talking about Kubernetes and how it's sort of the way it's built, the way kind of you have to access it is sort of adding complexity to this. I cover this in my graduate level project management course where you get all these different things that are going on in your project or in a like maybe in an IT environment, and you try to make things easier, and a lot of times in doing so you make things harder. So Kubernetes is kind of trying to make things easier for people for cloud services and that, but it actually ends up being pretty hard to pretty complex. So that was kind of interesting. And then this is another interesting thing, I think, also from Blue Sky. This is Complexity Cat. And this is an interesting bibliometric kind of, I don't know if anyone's followed up on this, but it's looking at the number of publications for autopoiesis and the number of publications for M, R systems. So MR systems are something that was proposed by Robert Rosen way back like in the 1950s. And they're these systems that describe, physiologies, interested in systems physiology, and interested in these different types of complementary systems or systems of mapping. He did a lot of things with relational biology, so there are different sets that are related together, and they form this system. And it's it's kind of one of those areas. It's kind of a niche area. And this is from data from the Web of Science, so I'm not sure exactly how they got these search results, but they basically are so the number of publications for autopoiesis goes up over time. Of course, autopoiesis is something that was developed by Maturana and Varela in the 70s. And you can see that it starts at 1990 and it goes up, from about 5 to about 20 until about maybe 2004. And then it starts to go up. In 2011, it goes up to like 45. And this ends at like 2011 or something like that. So this is, there's probably more to be said here, but we don't have the methodology, so I couldn't reproduce it. But it's interesting. MR systems, of course, this line is flat until we get to like 2004, 2003, and then you get these publications. So I was interested in this graph, and I looked into the MR systems references. And I found that, MR systems kind of were proposed in the 50s. There are a couple of publications in the 50s and 60s, and then the last one is like 1971. And then there isn't a publication from 1971 until 2003. So there's this huge gap in the practice of, talking about these kind of systems. And then after 2003, you get this growth in people using that model or that type of methodology for looking at relational systems. And so there have been a number of publications since then. I think the one in 2003 was actually autopoiesis and MR systems. So that, kind of combine the two, and then MR systems have been used in different biological settings, and the papers themselves range from methodology papers and putting, that type of methodology into code to applying them to biological systems. So it's really kind of an interesting mix of things going on there in that literature. Definitely, though, MR systems are pretty interesting. But I just thought that was interesting, given our discussions about cybernetics and autopoiesis and systems biology. Okay, so let me start off with an article here. We've been following this reading group.
It's Paul Middlebrooks.
Yeah, that one. Paul Middlebrooks.
I think he calls it brain-inspired complexity reading group.
Okay, yeah. That sounds about right, yeah. So that's brain-inspired complexity reading group, yeah. And they've been doing all these classic papers, and we've been following along. And one of the latest paper, I think, is coming up. So go ahead.
Yeah, it's Minsky. It's David Krakauer's like complexity papers.
Okay. Yeah. Yeah.
That's the reading list.
Yeah.
Is comes from Krakauer's compilation.
Right.
So that's hence the name.
Yeah.
Yeah.
And so the next paper is on Minsky paper from like the 60s. So this is one of the participants in the reading group, Darren Lott, and he has this blog, and he posted this blog post. I wanted to go over it a little bit just to see what his point of view is, because he seems like he brings up some interesting comments in the reading group. So, okay. So this is Kingdom of Mind, Path to AGI Ends in a Cornfield. And so he starts off in 1956. The pioneers of artificial intelligence declared machines would be able to use language, form abstract concepts, solve the kinds of problems reserved for humans. And they thought significant progress could be made in 2 months by 10 handpicked experts. That was off base. Two of these handpicked experts, John McCarthy and Marvin Minsky, went on to initiate an artificial intelligence lab at MIT. They were among the first but not the last scientists to grossly underestimate the effort involved and to provide a hilarious set of predictions of sentient machines just around the corner. So yeah, the first, of course, GoFi, or the first attempts at AI, were sort of thinking in terms of expert systems. Like if you could capture the expertise and, just kind of regurgitate it, it would work pretty well, So that was, they weren't wrong about expertise. You do need expertise in intelligence or in artificial intelligence, but the way that they approached it wasn't particularly fruitful. And so then they started their own labs and started to do research on symbolic AI and things like that. By 1957-58, the seeds for the greatest division in AI had already been sown. So this is symbolic AI, as exemplified by Newell and Simon's General Problem Solver, which was in 1957, and probabilistic AI, as exemplified by Papert's perceptrons, 1958, later marketed as artificial neural networks. By the 1980s, the symbolic AI movement had stalled, and after a very late start, probabilistic AI had also stalled. Over a half-century later, neither approach has even provided definitions for their highest goals, intelligence and consciousness. So this is kind of, these are the two kind of components of GoFi as it kind of came to be known. And this was kind of at the end of the 50s when symbolic AI and probabilistic AI were kind of formed. And so basically there was a lack of definitions here where it's hard to know kind of what exactly they're trying to accomplish, if they're overlapping domains or if they're separate domains. So he says, by the end of the article, I will tackle defining both. So he starts with the Turing test, which is that one of the earliest and most notable predictions about the eventual human-like abilities of machines comes from Alan Turing in 1950. So this is the quote here. I believe that at the end of the century, the general educated opinion will have altered so much that one will be able to speak a machine's thinking without expecting to be contradicted. So this is, Turing made some predictions about the year 2001, and these predictions were comparatively modest. The term AI had not yet been coined, and Alex conjecture is merely about machines thinking 50 years in the future. This is a far cry from predicting a conscious, malevolent, artificial superintelligence, or ASI, and we'll get to that prediction soon enough. Turing's benchmark, of course, was the imitation game. In this parlor-type game, a man and woman would be segregated from an interrogator who submits written questions to them. The goal of the woman is to be perceived as a woman. The goal of the man is to submit answers to the interrogator such that he would be fooled into thinking the man was a woman. So Turing's imitation game is, can a man trick another man into thinking he is a woman? And then the language in the paper is unambiguously gender specific. So Turing then proposes that the role of the trickster can be taken by a machine which attempts to imitate the man. If the machine can fool the interrogator 30% of the time, the point about thinking would be considered proven. And so this was, in 2001, a chatbot named Eugene Gustman supposedly beat the Turing test by pretending to be a 13-year-old boy from Ukraine. There were mitigating factors to influence this positive result, but the year 2001 is notable. And then by 2025, GPT 4.5 was being identified as human 73% of the time, which is more often than actual human counterparts in randomized controlled Turing tests. So Alicea was invented in 1966, was included in the contest, and scored 23%, worse than the humans, but Alicea outperformed GPT-4o's 21% score. So Alicea, which was at the time, which is this year, almost a 50-year-old chatbot, was able to do better than GPT-4o. So it's interesting that, we have this older model that's actually doing pretty well on that. I think it's important to note again that Turing is proposing a test of thinking and not intelligence or consciousness. The test is a purely language-based performance. It's also an imitation game, and winning may not mean what some might want it to mean. Over text, fooling another man that you are a woman does not make you a woman. Over text, fooling human intelligence does not make the computer intelligent. And then 2001, a bolder prediction. So Stanley Kubrick, the director of 2001, A Space Odyssey, was fanatic about scientific accuracy for his 1968 film and hired many consultants. One of these was Marvin Minsky from the MIT AI lab. You might expect HAL 9000, a sentient AI that becomes paranoid and murders the crew, was Minsky's contribution. It wasn't. Instead, Kubrick asked, by 2001, do you expect that computers will be able to speak coherently? To this, Minsky replied, by that time their voices will be very good and nicely articulated, but I doubt they'll understand what they are saying. This turned out to be prescient and redemptive of the exuberance characteristic of a decade before, but it didn't deter Kubrick's vision for HAL. What Minsky did contribute to the final movie was inspiration for the design of the EVA pod. This is the EVA pod here. Right here we see the foundational split in AI, and Marvin Minsky is central to it. So this is about the AI winter, the first AI winter, I believe. I'm sorry, Dave. I'm afraid I can't fund that. So in the 1960s, Marvin began designing and programming the Minsky robotic arm to build things with blocks, a skill with which most children are adept. These challenges colored Minsky's work for the next 60 years. By 1986, he wrote Society of Mind, which extensively uses World of Blocks as an illustrative. By 2011, he conducted a 26-hour MIT graduate course surveying the state of artificial intelligence. Robotics examples are still front and center, and in the concluding lecture, he challenges the grad students to think about how to make machines smarter. As a former president of the American Association for Artificial Intelligence, it's telling that Professor Minsky asks about smarter machines, like the EVA pod, and not about emergent superintelligence like HAL 9000. So he's kind of more in the camp of sort of smarter machines rather than superintelligence. During the lectures, Minsky expresses disdain and frustration with probabilistic approaches to AI. He also warns the students against using neuroscience as a guide to design. That's interesting. When asked about the lack of progress in AI, he says it stalled in the 80s because all of the funding has gone into artificial neural networks, leaving only 12 people worldwide to do the required work of deciphering common sense reasoning. So the way he states it, the AI winter, one of the AI winters was because there was this funding imperative for things that were not what he considered to be AI. And there's Moravec's paradox. And so there's a quote from Society of Mind: in attempting to make our robot work, we found that many everyday problems were much more complicated than the sorts of problems, puzzles, and games adults consider hard. It was this body of experience, more than anything we learned about psychology, that led us to many ideas about societies of mind. So that's the quote from Society of Mind. So aside from monetary challenges, one of the biggest impediments to advancing artificial intelligence is labeled Moravec's paradox. It's named for Hans Moravec, who wrote a 40-page essay on the subject in 1976. A phrase capturing the essence of the paradox was popularized by Steven Pinker. The main lesson of 35 years of AI research is that the hard problems are easy and the easy problems are hard. Moravec's Raw Power and Intelligence essay asserts that the division between the easy things and the hard things is based on the timeline of evolution. Things that are hard for a computer are essential to living organisms, and so natural selection has had millions of years to work out solutions. These solutions are instinctual and seem free or easy. The seemingly hard things are recent man-made problems and don't have biologically prepared solutions. So they seem hard by comparison, but really are not. So catching a ball is easy for a child, a monkey, or a dog, but playing chess is not. The easy task is handled by highly evolved sensory and motor portions of the brain. The hard task requires reasoning and awareness. Like Minsky, Moravec believes that creating a path to intelligent machines is an engineering problem and can be solved by incremental improvements and occasional insights into subproblems. These subproblems, in the parlance of Society of Mind, are called agents, and Minsky writes, you can build a mind from any of these little parts. When we join these agents in societies in certain very special ways, this leads to true intelligence. Okay, so that, and then the quote from Marvin Minsky again, it's mainly when our other systems start to fail that we engage the special agencies involved with what we call consciousness. So this is that's kind of an interesting take on it, given some of the recent discussions on this. So then he talks about the origins of consciousness and the breakdown of the bicameral mind. Above is the title of a 1976 popular science book by Julian Jaynes. I add breakdown to the question of consciousness as the pinnacle achievement of an intelligent mind. And so a quote from Julian Jaynes, but there can be no progress in the science of consciousness until careful distinctions have been made between what is introspectable and all hosts of other neural abilities we have come to call cognition. Consciousness is not the same as cognition and should be sharply distinguished from it. Jaynes' position is that human consciousness is unique, a byproduct of language, and has manifested only in the last few thousand years. That's fun, but I'm not buying into it. What is more interesting, though, is Jaynes then necessarily posits an older, non-conscious human mentality, prevalent for the vast portion of history, which we will revisit shortly. And then I guess he has another post here where he provides a working definition of intelligence, plus revealing how consciousness is actually an illusion. I don't know if Morgan had any comments or questions about that.
I mean, it's some interesting backstory about Minsky's work with Kubrick.
Yeah.
Yeah, I mean, interesting things, and yeah, it's good to know that the complaint about funding allocation is a perennial one.
Yeah.
I don't know if I mentioned this, but I'm trying to think who posted this, but some neuroimaging researcher posted this thing from like 7th or 8th century Syria or Iraq, where the astronomers were complaining about their teaching requirements.
Oh yeah.
Saying that they couldn't do research because of their burdensome teaching requirements.
Right.
Yeah. Anyway, yeah, but yeah, still, still amazing what they did, and some of their guesses about the future weren't half wrong.
Right.
It's nice to know that they thought, or that he predicted that they would speak, but they wouldn't understand their speech.
Right.
I feel like that's sort of even 2025.
Yeah. Well, especially 2025, right? Like we have machines that are speaking, and like people are like, well, is that a real person, or is that, should I listen to that thing, that speech, or should I like just ignore it safely? Yeah. So yeah, he brings up the two distinctions of symbolic versus probabilistic. It's nice to know that distinction was deeply embedded in GoFi. That you have these models, these symbolic models, of course, that were trying to achieve different things from the probabilistic models. The probabilistic models are, of course, what are sort of predominant today. But the symbolic models, you think, well, maybe we've learned how to do this better with probabilistic models, but it seems like the symbolic models are doing something else, and we didn't necessarily get the same developmental trajectory of those types of models.
Yeah.
So that's interesting. And then this idea of super intelligence versus smarter machines. So if something is super intelligent, it's like Hal, and then a smarter machine is, something else. So I don't know. I've not followed the superintelligence debate or the superintelligence literature, but I'm curious about that distinction as well.
Yeah, I mean, it's one of these things. Isn't that is that Bolstrom's term? I mean,
yeah, I think so. But I've heard people throwing it around.
Yeah, and yeah. So I mean, my fear with it is that it's too caught up in the kind of AI doomerism, which I forget who was talking about this. Maybe this was Emily Bender, but that AI doomerism is a weird sort of is kind of like this. It's related to something that Cory Doctorow talks about, which is that these companies want us to think that they're capable of superhero like abilities, you know, and that the
it's actually part of the same marketing effort. Well, no. Um, I'm trying to think of the kind of like most cynical way of seeing it, where it's like it's actually a part of the same um, sales pitch. That you know, that we're working on something that's so powerful it could kill you. You know, like yeah, it's sorry, it just makes me think of the movie Scrooged, um, with Bill Murray, where he's got the he he wants the ad for the upcoming Christmas Carol preview to be so scary that it kills people. You know, like this is the you know that this is you know, he's like, I want you to be afraid not to watch it, you know, like, and anyway, but the point being that like, you know, that back to this kind of like they've got $1 trillion reason for misleading you, and you know, whereas like the more interesting thing that I think somebody was talking about was just again something that Gary Marcus brought up at the this was like a couple years ago where he did a conference together with or like a workshop together with Emily Mender where they just invited linguists to talk about the interesting ways in which the language models failed. I don't know if you remember that meeting. I'm trying to think what they called it, but somebody talking about um, recently this week, you know, like because of course, you know, like still 100 papers will come across my feed somehow in terms of you know AGI or something like that, reasoning models, right? And they're just talking about how I think you know how interesting it is to actually track reasoning models in terms of how many um, how many kind of linked uh, not thoughts, but what would you call the how many steps can you chain before you get a real collapse in the model performance, and finding that that model collapse is always like super steep. So it's there's something strangely catastrophic about kind of like the last step, um, which again just points to this like I mean I don't know if these are you know silly character like these seem like much more interesting points to be playing with in the um, evaluation and discussion. Whereas like super intelligence gets so easy to fall into this kind of like I can imagine this. Oh, yeah, okay. Um, it was from the foresight meeting this week. So the foresight meeting was a neurosurgeon speaking about will AI ever replace a neurosurgeon? So perhaps not surprisingly, he was on the no or no time soon. but it was a really interesting discussion of what is involved in neurosurgery and how certainly for AI that it's a strange, it's a difficult marriage of both um, AI ethics in terms of um, so he was giving you a scenario where there's a piece of tumor that's left um, on a blood vein or blood vessel. So he's talking about the the scenarios that you have in terms of, well, if you leave any of the tumor, obviously you could be right back doing what is a dangerous surgery every time you do the surgery. Even with things kind of out of your control in terms of infection, in terms of complications, right? Together with this kind of minuscule amount of tissue that's left on a blood vessel, and the the difficulty of the actual physical removal as being an incredibly delicate, soft body complex problem where you both how you remove the tumor piece as well as like how to negotiate with its connection to the vein itself being a remarkably difficult soft body embodiment understanding problem. But that's something that embodied agents understand much better than we currently know how to uh, teach robots. And his point when people were saying like, well, isn't it possible with if I do this and I have this data set and this data set, and he's like, well, I think what you're doing is you're making an argument based on, can I imagine that, you know and he's like, I can imagine that. um uh and like it almost comes back to a similar kind of human problem where it's just this like, we have this ability to imagine things that actually aren't possible. And so now our problem is distinguishing those and trying to quantify those. Which seemed to me to be an actually interesting way to talk about kind of AI doomerism, which is that we have this ability to imagine it, um, um, but very like putting numbers on these things um, is something that we're actually really bad at. um, and he had some. It was a wonderful, like you know, it, it was really nice because it was like someone whose talk s- suggested that it was going to be a kind of technical, um, a technical discussion, um, but it was actually a remarkably human. Uh, he actually brought an incredible amount of humanity to the problem and said it as a very difficult, like it wasn't kind of like he wasn't setting a kind of trolley problem ethical dilemma, but um was in fact really giving you a great understanding of how difficult it would be to truly quantify so that an AI system would be able to probabilistically manage the problem. And it's like again, like it wasn't that he felt that this wouldn't be sometime possible in the future. But I think he was giving great grounds for like why this is not possible in the short term, as well as talking about mm, mm, critical mistakes that he made as a doctor, and sharing those with us, and sharing the um, after you make one of those mistakes, how does that color your next crisis? So he talked about kind of like how your continual learning is shaped by your potentially by the order of your successes and failures in a interesting, like, he's talking a little bit about judges being more likely to give guilty verdicts when they're hungry. Problem too, anyway, it was I'll see if they've got a link to that later, because um, yeah, obviously part of what he's talking about is the is um, the big action data set problem, where it's just like this is something new that is needed to really kind of give systems an intuitive sense of embodiment and physical manipulation. But I think he touched on something um, uh, uh, something actually more human than just this dilemma of he wasn't trying to frame it as a, would you want an AI to kill you, or would you want a doctor to kill you? Excuse me. It was it was really about how to what is the right way to train the system to respond to these to yeah, to these, say um uh, to killing a patient, like what would be the right way to have the system respond, right? So should it be less likely to engage in that task or more likely, and on what basis would you properly make that?
I'll try and find it.
Yeah, so that's really interesting stuff. Yeah, I'd be interested in the big action data set problem as well.
Well, I mean, this is what is driving. This is the new thing in Silicon Valley.
Oh, really?
Right? Is and so you see, it's just like I've got people front or not. It's not Frontier Towers sharing this. Um, People in these kind of startup founder groups sharing links to all sorts of kind of like very specific mechanical Turk operations where they're paying people in countries where you can pay trained people,
Right.
you know, at scale to basically be folding clothes with GoPros on, you know,
Oh yeah.
right?
To get the data, yeah, visual data.
And you know, like again, it's interesting to kind of embed yourself in San Francisco startup culture, where you know, this is what big companies like physical intelligence are trying to do, and that's how they're trying to do it, right? Like how can we get the ImageNet like data set that allows us to train this, right?
Yeah.
But somebody talking yesterday, it's a neurotech mixer, saying like, oh yeah, you know, all these big hedge funds and, you know, Chinese banks looking for neurotech investment are interested in EEG again, because somebody's paid for kind of like 100,000 hours of EEG data from, or you know, they're getting again like new types of data at scale, where they're literally paying for them, you know, and trying to solve the problem by collecting the data. You know, even though none of these are actually at like all extant text level that the large language models have benefited from, but yeah, but this is the big data. I mean, sorry, big action
Okay.
push that's going on right now.
Oh, okay. So this is something that they're just kind of trying to get training data basically for embodiment or for action.
Yeah,
Yeah.
but with this, you know, but using these AI valuations that they have, where it's just like, hey, you know, like you can actually raise, you know, $1 billion, and be spending that to just essentially buy data and compute, you know, with this hypothesized, you know, insight that will come from the you know, just self-supervised learning on enough data.
Yeah.
Yeah.
And it's not, yeah, and this is, of course, a distinction between probabilistic and symbolic training. We're putting all our eggs in probabilistic, actually extracting probabilities from images. Yeah.
Well, you know, so yeah, how you bring that into the real world is interesting. But I think you know, it's always good to follow the deep mathematics, if you will. I mean, in terms of like DeepMind's latest paper on its approaches to extending mathematics, right? Because it's like there you have a combination of I mean, it's hybrid systems to solve math problems, right? So certainly one of the outputs is like one of the outputs you're going to get is a formal lean implementation, right? Like lean for the package. You'll get a theorem prover output, right? So to some extent that is the new. This is one way in which you bring symbolic logic into um, into these systems, and even if they're using a combination of other kinds of techniques to actually generate that lean program. So like I haven't dug into it. It was just like yesterday that they had the paper, but they're using alpha evolve, they're using alpha, they're using multiple alphas in terms of techniques to extend new mathematics or solving extant problems and extending mathematical fields.
Well, it's interesting stuff. Yeah, glad to see that. Um, all the new things kind of emerging right now.
Yeah. Yeah.
Yeah. Okay, why don't we move on to? We had a couple things in the Slack. This is one of the things. I think this was something Morgan posted on from the archive on this idea of the Dragon Hatchling, the missing link between the transformer and models of the brain. And so, a couple weeks ago, we talked about this sort of link between like these machine learning models and models of the brain and some of these things. And this got posted. So the Dragon Hatchling is kind of a provocative title. But what do they mean by that? So let's see. This is from, these people are from Pathway, which I guess is a startup in Palo Alto. I'm not familiar with it, but that's kind of where they're coming from, is from a sort of maybe a tech startup standpoint. So the relationship between computing systems and the brain has served as motivation for pioneering theoreticians such as John von Neumann and Alan Turing. Uniform, scale-free biological networks, such as the brain, have powerful properties, including generalizing over time, which is the main barrier for machine learning on the path to universal reasoning models. I'm wondering why they're using uniform and scale-free as descriptors of the brain. Maybe we get to that later, but we'll see. We introduced the Dragon Hatchling, or BDH. I guess maybe Brain Dragon Hatchling. I don't know why they put the B in there, but a new large language model architecture based on a scale-free, biologically inspired network of n locally interacting neuron particles. So this is a network model. It's scale-free. We have these particle systems that are locally interacting. BDH couples strong theoretical foundations and inherent interpretability without sacrificing transformer-like performance. BDH is a practical performance state-of-the-art attention-based states-based sequence learning architecture. So this is states-based sequence learning is the key here. In addition to being a graph model, BDH admits a GPU-friendly formulation. It exhibits transformer-like scaling laws, so we find empirically that BDH rivals GPT-2 architecture transformer performance on language and translation tasks at the same number of parameters, 10 million to 1 billion for the same training data. So 10 to the 6th or 10 to the 7th to 10 to the 9th parameters. BDH provides theoretical foundations for understanding model behavior in the limit of large size and reasoning time. Our results, formalized as a chain of reductions of expressiveness in the framework of computational complexity theory and distributed computing, and combined with findings on the BDH model, show a macro to micro correspondence of function between the general attention mechanisms in state-of-the-art language models and attention mechanisms observed in the brain. So they're actually able to get this sort of correspondence of function between the two. I don't exactly know how they determine that, but these attention mechanisms formally converge as close-formed local graph dynamics at neurons and synapses, the equations of reasoning. So they basically build in, this is something that this is kind of an emerging theme in the literature, where you're using these closed and open graphs. So like, you'll have a graph where it's connected, and that's a closed graph. And then an open graph is where you need to insert a node to get a certain relationship. So, you can use closed form graphs to describe things. You can also use open form graphs to describe things. And, it's basically, if you have the graph itself is the representation that you have or the data that you have. If you can describe what you need with the data that you have, that's great. That's a closed form graph. If you need additional data, or if if the graph needs to add a node to get that kind of description, then that's an open form graph. So I kind of go over that in this spatial intelligence talk towards the end, and looking at the work of Saffron et al. On they're doing some things with open form graphs, and kind of go through that a little bit. So that's kind of an interesting theme to follow up on. So it's interesting, they call neurons and synapses the equations of reasoning, or at least these graph representations of neurons and synapses the equations of reasoning. You put it in quotes because that's always good. BDH can be represented as a brain model. It contains N neurons organized as excitatory circuits and an inhibitory circuit with integrate and fire thresholding of input signals at neurons. The working memory of BDH during inference entirely relies on synaptic plasticity with Hebbian learning, using spiking neurons at potentiation scales of minutes for the brain, up to hundreds of tokens. We confirm empirically that specific individual synapses strengthen connection whenever BDH hears or reasons about a specific concept while processing language inputs. The neuron interaction network of BDH is a graph of high modularity with heavy-tailed degree distribution. The BDH model is biologically plausible, explaining one possible mechanism which human neurons could be used to achieve speech. Then BDH is designed for interpretability. Activation vectors of BDH are sparse and positive. We demonstrate monosemantically in BDH on language tasks, including representation of concept abstractions, which happens even for small models below the 100 million parameter scale. Interpretability of state, which goes beyond interpretability of neurons and model parameters, is an inherent feature of this architecture. So we believe BDH opens the door to a new theory of thermodynamic limit behavior for language and reasoning models, with the ultimate goal of probably approximate correct or pack-like bounds for generalization of reasoning over time. So they have a technical blog entry and a GitHub repository for this. And this is their company pathway. So the abstract kind of reads a little bit like marketing materials, but also has some very nice things in it. These promising things. So this is they have a table of contents, the introduction, and then BDH, a language model architecture given by local distributed graph dynamics. This is exciting to me because they're actually using some elements of network theory here to describe some of the things that are going on in this. So, we're talking about different graph formalisms, first of all. And, we're using these graph-based language models. We're also defining this approach BDH as a local edge reweighting process. These are what they call the equations of reasoning. Interpretation of attention is a micro-inductive bias of reasoning. Interpretation of BDH as an oscillator network toy model, and then expressing BDH using brain models. And then, so that's kind of maybe the heart of the paper that I'm interested in personally. There's also BDH GPU, a tensor-friendly version of the BDH architecture, so they about implementing it on a GPU. Actually, they have the state space system definition here, the local interacting particle system, and then preserving parameter and state size. Then they have some section on scaling laws, the emergence of modularity and scale-free structure, linear attention, sparse positive attention, and monosemanticity. Then playing with the hatchling, where they're doing model merging, and training without backpropagation through time. So yeah, then let me go down and see if they have some figures. So yeah, this just shows like tensor-based models where you have centralized computing versus local graph models or distributed computing on graphs. So this shows the attention mechanism, local dynamics, and this feed-forward network. So the tensor-based models, which is indicative of centralized computing, you have the transformer, and then this BDH GPU. So they compare those two for the tensor-based model. So this BDH GPU is actually a different type of model than the BDH that they talk about. So in a transformer, you have a general attention mechanism. The attention mechanism for the transformer is a KV cache. For the BDH GPU, it's a state matrix and neuron dimensions. Then the local dynamics for the transformer is a linear algebra. For BDH GPU, it's a local mean field dynamics. Then the feed-forward network for the transformer are these MLPs. And then you have these weight matrices. And then BDH GPU, you have this emergent network defined by decoder-encoder matrices, and then these neuron dimensions. So they kind of use, I don't know if they're using reservoir networks or what they're using for this, but we'll maybe get to that later. The local graph models, on the other hand, and then, okay, so that's the tensor-based models. There's this general attention mechanism that they're trying to approximate here. And then local graph models, we have the attention mechanism, the local dynamics, and the feed-forward network. So local graph models are distributing computing on graphs. So we talked a little bit about how they're using sort of complex networks instead of neural networks for this, or at least the way they're describing it is more in the complex networks domain. So BDH, for the attention mechanism, is synaptic state plasticity, and there's a parameter for that. And then synaptic state plasticity is also the case for brain models. The local dynamics consist of local graph dynamics plus edgery weighting for the BDH. And then brain models, we have spiking graph dynamics plus Hebbian learning. And then the feed-forward network for the BDH are neuron interaction graphs. And so there are these graphs here defined by X, Y, and S. And then for the brain models, the feed-forward network consists of neuron interaction graphs, which are unspecified. So these are general overview of these architectures. The inference dynamics of BDH and BDH GPU act as a natural bridge between transformers and models of the brain. The two main inference mechanisms of a reasoning architecture, attention and the feed-forward network, are defined at a macro level through tensor operations for the transformer, and at the micro level, neuron interactions through local graph dynamics for brain models. The new BDH GPU architecture is naturally defined both at the level of vectors and of particle dynamics of neurons and synapses, acting as the bridge between the two approaches. Okay, so this is the physical system representation of BDH as a physical graph toy model. So this just shows these different graph parameters, GX, GY, and GS. You see them here. I guess there are connections between these different states. You have X and Y as the activation vectors, and then you have synaptic state of model. So the graph parameters of the model. So you have, first of all, you have state equations, and then you have the oscillator network toy model. The state equation for our graph parameters of the model. In the oscillator toy network model, the correspondents are wires, prods, and elastic connections. So that's what they have here. They have these elastic connections, wires, and prods. And then the synaptic state of model corresponds to the displacement of elastic connections and the oscillator network toy model. So this is the toy model, and I think what they're trying to do here is diagram out these different components. And it's kind of like they're taking things from their state equations and kind of translating it to this sort of graphical model. So you have these elastic connections, then you have the displacement of elastic connections, then activation vectors, the state equations, the correspondence of that in the toy network, oscillator network toy model are pulses at nodes and state correction. So that's what they're kind of describing here. Okay. So they have a lot of equations in here I'm not going to go through. And this is neuron-neuron communication using graphs. So this is the correspondence between graph H, which is here, with M edges, which is on the left, and neuron-neuron interaction graph G, which corresponds to H squared. So basically, this just shows how you can express linear signal propagation on a broad class of graphs using 2 steps of linear dynamics on a sparse circuit. So I'm interested in this toy model, and the toy model, of course, is usually, we'll use a toy model in physics to demonstrate a principle that's kind of hard to understand, and you build this small model that isn't necessarily useful for large amounts of data, but nevertheless it communicates this idea. So I want to go over the definition of the toy model because I think it's interesting. So we will consider the toy model of an n-particle system shown in the figure that I showed in figure 2 is an illustration of the general form of dynamics of the state space equation of PDH. All right, so the first thing is we draw n particles in a circle. We see that here we have the 5 particles. And then the particles are connected with each other by the state elements, represented as these elastic connectors, these wiggly lines. The topology of the pairwise connections is given by the graph GS. So that's the black lines between the states, and may in general be dense. The signal displays dynamics of state P through or phi through tension on connectors, which evolves at a slower time scale and a more pulse-like activation dynamics, XY on nodes, appearing and vanishing regularly at a rapid time scale. So that's kind of what they're doing here. So they basically have these elastic connections between the nodes. Then they have this tension that introduces these pulses, and that's kind of how they're imagining their network. The slower state dynamics represent in the first order oscillation or relaxation of the system of elastic connectors. Once an elastic connector between particles I and J has had its endpoints displaced through states X and Y, respectively, a tension appears on this connector, which causes its displacement. And so then, between the particles. So there's this displacement between the particles when you get this sort of tension in the system. So it's like kind of combining a physical system with the actions of like a spiking neural network or something where there's some sort of synapse or connection between the two neurons. So it's interesting. And, we've talked in DevoWorm, we talk a lot about tensegrity models. And this is almost kind of giving me the same kind of idea about how those models work. We have a number of nodes in the model, which are mechanical points of articulation. And then we have these strings that can induce tension or, some other physical constraint. And they behave in a way that, introduces superstability to the system. So the physical forces balance out. That seems kind of like what they're trying to do here in a way. They're trying to build this physical system that represents kind of the, what you might see in a neural system. And I know there are a lot of like analogies being made here, but I think they're onto something because there are a lot of these sort of thermodynamic approaches that people are starting to pick up now in the field. And so, but it's interesting how they're trying to kind of find the right mix of things. So the faster dynamic, back to this definition of a toy model. The faster dynamics represent the node dynamics of particles. Over time, pulse displacements xi happen at nodes as a result of either previous behavior of the system or perturbation by an external forcing field. Okay, so this field would be a language input, or it could be some other type of thing that you're trying to analyze, like data for classification or something like that. A node I with displacement xi may, due to the exaggerated action of tension of elastic connectors adjacent to it, activate a system of prods gy adjacent to it, perturbing nodes it hits in this way. If another node j is prodded sufficiently hard, it may cause it to activate a perturbation yj. Perturbation yj of a node j will, in the next step, propagate action to those other nodes I prime, which are connected to j by a system of wires. Yeah, this is definitely sounding like tensegrity. I'll have to pull this up, or at least think about this in that context. Because in tensegrity models, you have single nodes that interact with other nodes, but you have both these direct connections and these indirect connections, or at least indirect effects that you see. So node I is connected to node j, and then node k is also connected to node I and node j. And when you perturb I, or when you perturb a connection with I, it perturbs the connection with j and k, and then that propagates back to I. So you get this feedback as well. So you get this mass set of effects from a single propagation, and that's largely due to the connection. They're all being connected in a network. If the aggregated pull of wires on a node I prime is sufficiently strong, this modifies its pulse displacement xi prime. The pulse activation yj prime of some node j prime directly following the pulse activation of xi prime of node xi prime results in an increase in the tension of the connector ij, adding to the value of the tension. All pulse activations y subside and the pulse propagate, consequently altering the slow state. So this is kind of describing how these relations happen in the network using a very simple set of interactions that we can unpack. So I like that, that aspect of it. I'm not quite sure about if I can answer my question about the type of methodology they use for network. I don't think they use any sort of reservoir network here, but it would be interesting to use that to grow the graph. They do use edgery weighting, so they use a closed graph with edgery weighting. I think that's what they're doing here. They also have this sort of anchoring definition. So for anchoring in the literature of dynamical systems, we note that already systems following an interaction kernel with a strongly constrained K in the form K inclusive of Ij exhibit powerful nonlinearities, which is what we talked about before in the toy model example. With such a restriction on K, equation 3, which is up here, this equation, which looks like a replicator equation, describes the class of evolutionary systems following the equations of replicator dynamics. And this was from Hofbauer and Sigmund, also equivalently known as non-normalized form of the fundamental Locke-Volterra predator-prey dynamics. So this is a replicator equation here, which describes sort of, where things replicate based on their fitness, and if one class of replicator is dependent on the other class of replicator, they sort of regulate their reproduction and their ability to replicate. Replicator dynamics can naturally be represented as graph systems whose parameters are defined on edges on the graph, but whose state is updated on nodes on the graph. So the parameters are edges, the states are nodes. By contrast, when defining dynamics for reasoning in the current work, we will also need to capture a more powerful class of graph-based systems where, crucially, State is larger than the number of neuron nodes appearing on neuron edges or synapses. Okay, so I think that's all for this paper. I don't know if people had any comments on it, general comments. I think getting any more deeply into the methods is not going to be useful for understanding it. But they're bringing together a lot of things here that are not like typical large language model or machine learning methodologies. Yeah, good paper. Yeah.
Yeah. So really appreciate you going through it. It was, I don't want to say given to me as a task, but it was put forward at the tower by someone who I should say is not a machine learning researcher,
Okay.
but she was kind of putting it forward as like something for both the AI group and the neuro group to look at as an interesting as an example of a post-transformer architecture.
Right.
Now I'm gonna leave aside some of the editorializing that I think that she added that I don't think is I don't think I get from the paper. Excuse me, sorry, awful thing with her. But it there was just also some weird things about the paper too, right?
Yeah, it didn't seem like it was implementable. Maybe.
Whereas it's just like. So background on the company, it's like it's a logistics company, right?
Okay.
So as like anything I can find in terms of this company and or the researcher involved who definitely has technical background to be able to propose things,
right?
But like again, it's something where they're really coming out of kind of like operations research.
Yeah.
And which does have a certainly has a long and storied legacy. So but then there's things where it's just like I don't know whether I need to concede to them just some poetic license in the sense that like it's hard to stand out in the fire hose or
Yeah.
just massive tsunami of papers.
Yeah.
In terms of baby dragon hatchling, like I don't know where that comes from.
Yeah, I don't either. Oh, it's baby. The B is baby. I thought it was brain, but
it's baby dragon hatchling.
Okay.
And I think it's supposed to recognize that this idea has hatched.
Oh,
like what you're looking at is the hatchling. I mean, a baby
okay.
hatchling now. I assume that means that there was a previous paper.
Well, yeah, probably more theoretical. Yeah. I mean, this is theoretical. Yeah, but
right. But then it comes down to this kind of like what does the transformer architecture represent?
Right.
In the fact that like all the big language models are using much more hybrid systems now. Or like they're using transformers, yes, but they're using plenty of other, if you ask somebody to characterize any of those models, like that is just one of several things that you would use to characterize them,
Yeah.
And I think this somewhat points to the fact that wasn't the goal of this paper.
Right.
Like is this a post transformer architecture, or is it literally just a brain inspired architecture that should be absolutely, like it's put up against transformer, but not as like necessarily as like this is post transformer, as being just like this is different.
Yeah.
And kind of set to have it's trying to optimize different things. And so again, I appreciate this discussion, because it's just like she would like us to do a more general meeting on post-transformer architectures.
Okay.
And my question is, obviously, we follow a bunch of neuro AI, projects and workshops and researchers, but and this kind of goes back to that remember that big kind of position paper on neuro AI that like Tony Zader, I think, is either like first author or last author on.
Yeah, I remember. Yeah.
It's like a couple of years ago. And then like David Fowl, like PFAU,
yeah.
I think he's like a DeepMind guy, was kind of slagging off on Twitter and saying like this is these are I forget, he had harsh words, because he was just like we're inventing the future, and the future is ML, or the tenuous brain metaphor is not actually important. And it should be, it's going to come from the math, and it's optimization, and like if you're interested in neuro AI, like you're really doing something else. Like it's again not clear if you're actually theorizing about how the brain is organized.
Mm-hmm.
Like is neuro AI a practical subdiscipline of ML, or is it actually a subdiscipline of brain science, where you're actually making you're positing a kind of theoretical model, or not theoretical. You're positing an architecture, and kind of seeing the computational consequences of that, in the sense of playing, making toy models, having it work on data, and kind of seeing like, oh, let's see the interesting things. Let's see the interesting features that this approach has. But it's not meant to be a competitor to like production ML pipelines. Does that make sense?
Yeah, it's like you have the theoretical models of the brain. Then you have kind of maybe a way to think about it in terms of an architecture, which might be more applied. But you don't want to go up against like super performing models of that might be used in industry.
They're really two different programs.
Yeah, they're not the same type of aim, right?
Yeah, it's like, yeah, and anyway, it's like this is So again, thank you for covering this paper. Selfishly, I posted it because I was just like, I was kind of like, what would you do with this?
Yeah. Well, I was fascinated by the title. It makes maybe more sense now, maybe even less sense when you said baby.
And that seemed to be, and that's like again, like I think they absolutely know that's they knew what they were getting with that title.
Yeah, attention. Yeah, which is what they're trying to model.
Yeah. Yeah, and so it's like it seemed to me also being like, again, like if I was trying to pitch in Silicon Valley, this could be an important. I like always impressed with people who are good at selling a narrative, and So, sorry, I'm cleaning my dogs here. But yeah. So thanks for covering it. It did seem to be kind of like an eclectic mix of things.
Yeah, it was definitely
approaches and yeah.
Now I like the network part, like kind of getting away from like the neural network and getting into the complex network stuff, where you're thinking about like graphs. So you have the graph, like it's kind of a conduit to graph neural networks, but they don't talk about graph neural networks. It's kind of like going to something like a growing graph where you're adding nodes in, you're connecting them up, and then they're eventually forming this sort of architecture, which could be scale free. It could be what we call small world. It could be random. The graph properties can vary based on like maybe learning or maybe some physical constraints. And then of course you have thermodynamic constraints, because you have these elastic. They model like synaptic learning as elastic connections, which is interesting, right? Like it's you have this analogy between elasticity and like synaptic encoding or synaptic adaptation. Which also, though, when I just mentioned about tensegrity structures, which are something that we're talking about in DevoWorm to model biological superstability. You have this same kind of architecture or a similar architecture where you have this network of nodes, and there are these physical things like struts or other types of physical structures that are biological in this case. And then you have elasticity, which are the connections between the nodes. You have the elasticity between the nodes, and so that's usually a physical medium in tensegrities. In this case, it's an analogy of synaptic learning, but in a physical biological network, it could be adaptation of some type, where you have the adaptive mechanism that is where the body or the biological system experiences something, and it gets encoded in the configurations it can take on. So there are a lot of relationships with like thermodynamics and physics, a lot of relationships with biology and other types of structures, a lot of relationships with learning in the brain. It's very broad reaching, and I could see a lot of ways to apply these.
I would certainly appreciate any thoughts you have. If you were curating papers or kind kind of architecture that you'd want to put as post transformer. Like the first thing I always think of is like, well, there's two things. So one, I think of this old. I remember back in 2016. It's like it's not that long ago, but I'm talking about it like it's the Dark Ages. The Do you remember capsules? Remember Hinton's capsules? No? Okay. So I think this is like you remember when everything was GANs? Oh, okay. Take care, Vidhi. Everything was GANs, and I forget, it was like a year plus, like of Goodfellows paper, and maybe even I have the timeline wrong on this, but like the point being that Hinton put forward this new architecture that was the post whatever was the architecture of the day, right? And what it had is actually something that I think of as very Maxwelling, in the sense that like it was oh, okay. Yes, I will get that. I'll get that done today, Vidhi. Yeah. Sorry, she's just asking something in chat. Yeah. I got the link for sure. And the so I mean, I just mention it because like I remember. I mean, we've still got this discussion on our NeuroTechX Slack, where it's just somebody's asking like, "What do you think of this architecture?" And I was just like, "Yeah, it's cool." Like again, it reminds me now of kind of Max Welling, where it's just like it's utilizing symmetries. It's utilizing symmetries in some fashion. Like I can't even remember exactly now. But it's very very much in the Max Welling tradition, which leads Max Welling's group to kind of Clifford algebra approaches of it's like current architectures, but with Clifford algebra extensions, right? which again speaks to this kind of like geometric algebra understanding or exploitation, right? But they totally didn't take like nobody used these. like like this did not take over, right? Like everybody kept on using whatever it was. What did we use before? Anyway, like they just kept using whatever was the backprop approach at the time, right? And just say so the other approach being Mamba, right? So Mamba is supposed to be a post transformer architecture that it's supposed to improve on transformer architecture in some theoretical way, and I assume to get the paper published that they had to come up with a few examples where it was actually better, But the question I have though is like, what would those metrics be?
And in terms of like improving upon transformer architecture, you'd have
I mean, like would it be, like it could be in so many different directions,
right?
And I think it says something that we don't actually know which of those dimensions. That's like kind of valuable to explain, like to be better on,
Right.
In terms of becoming this bedrock algorithm that allows for, that again, like allows for a much greater, additional complexity after the fact. I mean, in the sense that like again, these large language models have have a bunch of additional training features and architectures to them in terms of mixtures of experts and things like that.
Yeah.
So somehow that, yeah. So again, this is more my own, or perhaps a defect of my own self-taught education. It's like self-taught training.
Right.
Is that like I can't fully understand what the like what are the important dimensions on which that evaluation would be held to, as well as like, yeah, or is there even like a greater kind of misunderstanding of my own in terms of what are the how the transform model itself became this like first pass that other things can build on.
Yeah.
And is there's something in, yeah, it's like
I have a few questions actually. Maybe that
please.
help. So I mean, why do we want to have a post-transformer architecture? Is it because we want to do better, or is it because it's maybe we want broader performance?
Totally, which it sort of goes back to the capsule thing, where it's just like I kind of felt like Hinton was putting out this capsule thing because it was supposed to be like it was kind of a way to grab to take the spotlight.
Oh,
right.
Yeah.
I super cynical, but at the same time, like again, like there's huge money at stake in these things. Like this isn't an academic. We're not talking about astrophysics here.
Yeah.
We're talking about what has potentially created the largest economic bubble of mankind's history, right? Like, so we're talking about a lot of money. And I don't want to fall down that in terms of I think I will say that the woman who proposed the baby dragon hatchling paper, I think, was definitely coming at this as an outsider, wondering like, are there architectures that would be more amenable to solutions to an AI alignment,
Okay.
to AI alignment issues, right? So which was maybe a misunderstanding of kind of like the brain inspired part. But again, it's like how yeah. Anyway, I think she was definitely sort of thinking of that, in the sense that like, how do we get away from an architecture that's just a sequence predictor, and that like that there's certain limitations to a sequence predictor.
Yeah.
Or like everything just being like trying to do sequence predicting better. And again, I think the Blaze Arcus. How do I keep forgetting his last name?
Arcus de Aguas or something like that.
Yes,
Arcus
yes,
e
yes,
Aguas.
yes. Yeah, you know,
and
like as someone who definitely cares about this, is like pointing out that you know, there are intelligence problems that are good sequence prediction problems, and then there are intelligence problems that are absolutely not. Sorry, got some people leaving here.
Yeah. All right. Yeah. And this is interesting because this gets addressed in the cybernetics paper that we've been working on. If you dig into it a bit, we have the kind of talking about different models, not focusing in any one model, but how models of the group regulator can help us understand some of what the structure of what's going on in artificial learning systems. So one of the things, of course, with large language models is that it's a sequence predictor, a sequence learner. It's spitting out these tokens that are putting things in a sequence, and they have to make sense. But the thing is that you can use a good regulator model to approximate that. There's a thermodynamics to like sequence production. There's also a link with DNA and RNA and proteins, because there are groups that have been using large language models to predict DNA sequences, to predict protein sequences, with pretty good. We covered a couple of those models in DevoWorm, where they do pretty well in predicting sequences, which is different from human natural language, because it's like, it's just trying to predict like a functional sequence. There isn't the same sort of people argue that there's grammar and that there's stuff like that in DNA sequences, for example, but the structure is different than a natural language, but it can still do that. And so at the core of a large language model is this sequence production, basically. And then you can use a good regulator model or something like that to, produce sort of the thermodynamic conditions of that. I guess that's kind of the argument.
Yeah, I mean, I'm just going to say Blaze.
Yeah.
I'm going to use his first name. Not that I'm on have a personal relationship. Blaze's point is it's certainly like that, where it's just like there's a sequence prediction works, but if the beginning of the beginning of the sentence is is something trite, like it's a where probabilistically you can guess what that word is.
Right.
That's great. But if the same sentence is actually the beginning of a mathematical proof, the next thing that you need to predict is actually unlikely, but absolutely can be constrained by certain bounds, or can be given a say a symbolic representation. I just wanted to say to that point, and again coming back to this, these are difficult topics because these are certainly tied to current economics. Was a wonderful video I saw of I'm trying to think of the CEO of NVIDIA. And it's like Wang, like Huang.
Yeah.
Anyway,
Jensen.
So he's showing off the new Blackwell architecture, DGX box.
Yeah.
Right. So this is like a $200,000 box. He's talking about. I think he's next to kind of like the head of AI for Germany. Not like a university,
right.
Germany.
Just the government, yeah.
Like, and they're like we're gonna buy 100,000 of these boxes, and he was talking. He's like, this box outputs tokens, and those tokens are money. Like it wasn't like it was just a pure these tokens. This is a money printing machine.
They're food pellets.
And I was just like, well, there it is. You can't get a clear pitch, right? So again, what is post transformer architecture, right? Is it so it comes back to this, like, is post transformer architecture just a specialized architecture where it's just like it's set up for math problems? That doesn't seem like what a post transformer architecture is. It's somehow fundamentally like what the model's outputting is much more powerful, right? Like it'll be something. This is kind of a stupid metaphor, but it'll be something like, instead of outputting tokens, it'll be outputting complex tokens. Like to follow the kind of mathematic, these aren't numbers; these are complex numbers.
Yeah.
Yeah. And it'll open up this new dimension. Like, that'll be the post transformer architecture, where it still somehow has the sequence prediction, but it has something else. It's somehow you get another. You get another layer of
whatever
solution.
It is that we need, yeah.
Yeah. But it's again, it gets to something fundamental about what this token is, right? Because it's like the token itself is
yeah, we need a higher level of organization for tokens. Like, a token is just kind of an atomized thing, and then you're putting them together.
I mean, the complex number idea is sort of, I mean, like the token is kind of like a Fourier, output. You know what I mean?
Yeah. Okay.
You are getting. You are getting this magical transformation of the data that you've given it, right? And then in this space, the data looks, and has this interpretation. Anyway, so I thank you for covering that paper.
Yeah.
You've given me a lot more to talk about in terms of trying to do an event around this. I mean,
yeah, definitely.
So it's and again, it comes back to this question of, what is the neuro AI program, and is it is it actually relevant at all to, should neuro AI remain a brain science discipline?
Yeah. I think
than pretending to be an ML discipline.
Yeah. Well, I think, in terms of benchmarks, of course, they're probably not going to be there for, I mean, if it does happens to do better performance-wise than existing AI models, so much the better. But I don't think we should pursue this in the sort of with the goal of optimizing performance on some benchmark. I mean, that's just not what you're going to get, at least not at this point. So it's really about building. To me, in my mind, it's building models of the brain or building models that are brain inspired, and it's just basically playing around with what the brain does, what are mechanisms we know. We know that there are certain mechanisms in the brain that produce maybe behavior or some sort of output that is, based on learning or some sort of intelligent behavior. And then, seeing what you can do with that. The application domain is maybe open. We don't really care so much about that. And it's not so much remaining in neuroscience, but it's not putting it up against like state of the art AI. So, what the artificial life community is doing is very similar to what I think is probably the goal for neuro AI, at least in the short term, which is to build interesting models, get interesting results, see what they can do, and if you can put them, build performance benchmarks and get some good performance on them, then that's great. But that's not that shouldn't be the goal of the to because what happens, of course, in state of the art AI is they're always trying to optimize the benchmarks. That's the whole goal, and then you're getting these small improvements, and you're like, well, this is great. This is better. This is a better model because it gives us just a little bit better performance. But then it's like, well, okay, but like, what is that? I could build like a model that's has bears no relationship to the brain. In fact, it's just kind of like maybe a brute force model or a random model, and I can produce a certain level of performance. What does that tell me? What's interesting about that? I mean, I guess it gives you good performance, but beyond that, it's not much. So I would definitely think, at least in the short term, neuro AI is about kind of brain modeling and seeing what you can do. But I would, it's you don't want to get caught in that trap either of trying to optimize metrics and things like that.
Yeah, I mean, for sure,
Yeah.
right? And we think of like a benchmark. Yeah, like again, we're so limited in our attention
Right.
that we can actually come up with a lot of benchmarks, and yet it still be very limited in terms of the space in which we actually operate, and so maybe just finish off with a last reference to that biological underpinnings of lifelong learning perspective paper that has the 30 plus co-authors. But the wonderful matrix that it has in terms of, these are the problems that we see in continual learning. And these are the mechanisms, the putative mechanisms that biology has found that can perhaps deal with some of these continual learning problems, right?
Yeah.
Because again, even in this short time, I forget how much the large language models don't try to, they are in no way, shape, or form any even attempt at solving continual learning problems.
Yeah.
Right. They are a very fixed model. Anyway.
Yeah, it's interesting stuff. Yeah, we'll try to come back to this sort of post transformer model thing too, because I think that's an interesting question. Even I mean, because you reason we use transformers is exactly why, because they perform well, or that they provide a compact representation. I mean, those are great and interesting, but like you could And especially like thinking about like language models. What do we want? What could we put in there? Maybe it's not the greatest performing model, but what would give the most interesting results? So we could substitute in a bunch of different types of models. Maybe things that are model attention. Maybe they're more computational models. Things like that.
As I mean, and potentially, and I think this gets to the root of her actual original request, which comes from so she leads the human flourishing floor.
Okay.
And I think, I don't even, it's not even, I think, I know that the only question I'm asked by basically every person who comes to the tower is like, I get all the other floors. What's the human flourishing? And but I mention it because it's relevant to the other Foresight meeting. Was it Foresight? No, sorry. It was Computational Philosophy Salon this week that had Adam Saffron. And I forget the other guy's name. I think it was a Finnish name. Yeah, it wasn't Ruben, but it was like it struck me as Finnish or Baltic. Anyway, I won't claim to be that knowledgeable, but he's moving to Oxford, and his group at Oxford is going to be called Flourishing Intelligence.
Okay.
And yeah, thanks, Jess. So it seemed relevant to the Lupin Laukkonen, Ruben Laukkonen,
Okay.
and the again the biological underpinnings of lifelong learning is really about autonomous systems. Systems like that are potentially sustainable, right? So, and I'm using that in a very broad sense, where it's just like they're both autonomous and able to update themselves. You can release and they will continue, learning and adapting and staying competitive, right? But can do so with resource constraints, etc. Anyway, it's this combination of his work as a practitioner of meditation, but definitely relates to something that I've seen Adam Saffron speak to multiple times when he comes to the Foresight Institute and talking about compassionate artificial intelligence. It's like somewhat speaking to this alignment issue and somewhat speaking to how to what role would AI ever have in our happiness and or and unfortunately, so Jess is saying, has Adam spoken about this? He absolutely had I don't think, I think you can find a talk of Adam's on this in terms of covering this. He has since he joined Levin's lab, I think he's done a couple of his own meetings where he's talking specifically about this. He's definitely spoken at Foresight Vision Weekend. I think it falls under existential hope. Like as you know, I mistook it. So in my head, I was just like, oh, this was a Foresight event, and I was like, no, that's actually, it was a computational philosophy salon. But I know he's done specifically his own meetings on this, and anyway,
I was only asking because I know the Foresight Institute is a concern about many things that I am, but I didn't. It's sort of like Venn diagrams not connecting, and then you're like, oh, like I didn't know Adam and Foresight were doing that together, because I know Adam's been doing a bunch of stuff, and I know Foresight's done a lot of things, and I didn't know there was like any, like. How that would work?
I wouldn't say, though. I mean, I should say that this was Adam pitching. So this was Adam coming to. The last time I heard him speak directly to this, I think, was actually the Neurotech whole brain emulation AI safety workshop, and it was pitch. I do think it's somewhat aligned with their existential hope program.
That's what I would.
But I don't believe he's like a fellow of that, for instance, or
right.
I could be wrong. But it's definitely it relates to is academically, I think he was an effective neuroscience.
Yeah, right. I was surprised. Like you were surprised that Adam it wasn't a Foresight. I was surprised because the meeting itself for me was like, okay, call for active inference stuff. That's how I was told about it, and then it's so up, and it's Ruben who's talking very,
Oh yeah, right. No, I agree.
Stuff. And then Adam's there. I didn't know Adam was gonna be there at all. I'm like, oh,
yeah.
Fun surprise.
I was expecting more active inference. And I don't know if they came around to that because I just had too much stuff going on at the same time. Unfortunately, we had a memorial service at the tower for somebody who passed. So I was not on for the whole time, but they seem to be doing a deep dive in meditation and issues of consciousness cessation and things like that are difficult, but again, I felt we're kind of easier to understand with differing anesthetics. If I was going to study them experimentally, I think I would be interested more in using different anesthetics and getting at some of the time perception and other issues that they were talking about. I didn't catch all of it.
I'm sure there's a whole bunch of things I'd say, but I imagine you want to get going, Bradley. I'm sorry for coming in so late.
Well, it's okay. We have 10 minutes left. Would you like to give an update, or would you like to discuss some things?
I didn't know at the meeting that I'm curious what happened earlier today in the meeting, because I don't want to repeat anything. I don't know if you guys talked about what Morgan just said or other stuff. So I don't want to rehash it. But
Well, we talked about this baby dragon hatchlings paper that was in the Slack. I also did
we humored me.
Yeah. Well, we also did a blog post on like AI, the underpinnings of AI, and this whole complexity reading group that Paul Middlebrooks is running. So you're talked a little bit in that space, and then I gave some updates for the lab. So yeah, I mean, I don't know if you had any general updates though you wanted to talk about.
Oh, I mean, I have a whole ton of things to say. Oh my god, I'm like remembering stuff continuously. I don't know where to begin with some things. One, I'll try to map it out very quickly. One, I have plot twisters related updates. I have Princeton and Vision related updates. I have JoPro Future Center updates, and I have updates around. I mean, I was at the salon that Morgan was at, which I'll start with there and just say really really interesting. I'm so glad I was able to go to it. I 0%. I thought Adam, when I showed up in Zoom and I saw Adam in the Zoom, I'm like, oh, that's cool. Adam's here as a participant. I haven't been in any space with him in a while. I came in an hour late, but he was like a co speaker. So it was very interesting to see him and what he's up to. I know he's doing like a small like consciousness journal club reading group thing that I've been invited to, and I've never been able to go because I've always been the time to doing other things.
That was what
I've had like he didn't disappear or anything, but to me he disappeared. So I haven't seen him or interacted with him in a long time. But it's such we're on the same path of a lot, still. Or we're in similar things, blah blah. So that was very cool, but also unexpected. A lot of the thing about the computational philosophy club and a lot of Ecolopter related things, Bradley, if you don't know, is like a lot of times they come up with like 1 or 2 days notice.
Yeah.
Like this wasn't planned like 2 weeks ago. It didn't exist. So it's kind of like this randomized opportunity thing, which is cool. But I would have loved to be like, oh, let's have all the Condition Futures folks come to this event, or like last week or whatever. There's also like a funny one next time. It's cool. So that was fun. Let's see. Plot twisters. The wheels are slowly turning. Plot twisters is demoing. They got a grant, or we, I suppose I should say, got a grant to do a very specific part of the game, like about through Metagov, and it's about it's called Small Hassles Court, and people are working on it. I'm not part of that group. It's kind of a little secretive. But they're demoing it, or they're having like a user testing thing happening, starting now, I guess. Like the next few Fridays they're doing something. So I will try to post that in the chat because it'd be good to have people to give feedback and whatever. And I don't have a lot more to say to that because I have no idea. I have no idea what it is yet. But that's happening on one side. On the other side, and working with another part of plot twisters stuff that I do know about has been we're looking at a certain part of plot twisters which I'm not at liberty to discuss fully, and its relation to things like emotion regulation, like theory and research around it. But also, there's a side thing that I've kind of been really focused on about pedagogy, teaching, curriculum, education. And it's led me down this pathway of, let's see, looking at classical works, even like critical classical works like Pedagogy of the Oppressed, which is like one whole lineage of thought and ideas, and more contemporary. I've looked actually at like pattern language and the concept of a pattern language by I think Alexander in that book and stuff like that, and then how to apply that to teaching. And so my latest like the latest turn of this path, which I would have actually spent a lot more time on here if I had more time earlier today, and maybe next time,
is how people are using it to map curriculum spaces. And for those who don't know, a pattern language is sort of attempting to demarcate in particular domains recurring patterns of how something materializes. It's based from architecture, but I'm super fascinated to apply it to other sort of a front like pattern matching pattern language plus frontier map, as you can tell. Or like we've talked a lot about curriculum design, epistemological directories. So kind of like what's going on there, and looking at some papers about like actual educators, curriculum designers, teaching teachers, pedagogy. That's really interesting to me. So lots going on there. The future center stuff is kind of related to that. Um, and more, yeah, I mean, directly related to like curriculum design. Like I'm really thinking about how, if I could do, we've kind of randomly have talked informally about like, oh, designing my own PhD stuff right now. Some of that would essentially be um, like how to develop certain new fields, but then how to do the training like as well. Like how are you like very both implementation and theory of how to do new stuff in that sense. So the future center is a little more concrete than that. But suffice to say, it's about thinking about curriculum design, thinking about different projects around that, and I'm really trying to talk to people in that space to kind of get a better grasp of things. And I should probably do a more broad update in the future center in general. Um, I've been kind of MIA from a lot of like intense work the last 2 weeks. I've been processing some things, a bit under the weather, blah blah blah. But this week was kind of a coming out week, and then I'll conclude on a very fun thing. Um, uh, what's that like Mark Twain saying? Like rumors of my death were widely, um, overblown or whatever. Um, Princeton Envision is alive and well, and to my surprise, I reached out to them months ago and heard nothing. And then I just got a random thing like 10 days ago from one of the co-chairs. And we've talked this week, we talked Monday. So I will very likely be a speaker at the event this year, which is in February or next year in February, 2026. And I don't quite yet know what it will be. It's a little bit different than events in the past. It's actually taken a step more in the direction in the direction of data and direction or society ethics technology. Like they've shifted to AI, tech policy, ethics, or kind of we robot feel even. But I don't quite know. Like it'll be, you know, I, I've kind of pitched a little bit of the idea of presenting on some current topics, but also like Princeton Envision historian because I'm such a fan of the three events I went to, as we all know here probably. Um, and kind of just doing this cross generational, like a lot of my the major theme for me of late is sort of this cross generational. We're massively intergenerationally unprepared for the moment we're in. So how do we foster cross generational? Let's try to help young people understand what is happening in the world, to be comical about it, but in a very serious way. Like I'm very happy to provide. Like they didn't have a lot of contact with the like Luca or Sonia Joseph, who were all Princeton Envision folks, no less. Um, Phil, formerly Phil, now Emil P. Torres, uh, and Logan Thrasher Collins. Like we were all Envision folks. All of were there, and so like there's I think they don't even know the depth of some of the legacy that they have. At least from an event space, but like, what does that mean for people? For kids, for people trying to understand and do meaningful things, which is like something I'm extremely focused on lately. Is like, holy crap! Like we need to like recognize the degree as educators or guides or mentors that's happening. And so I'm looking forward to that. I'm in talk with them about what to do. I have ideas and all this other stuff. But finally, I'll say uh, we're kind of wrapping up things with data and direction too. And this first summer cohort that's evolved in the spring cohort, and I'm just very excited with them. And some of the folks I stay with their projects the whole time, and when we're talking about grad school, like kind of like mentoring, like not mentoring, but like advising. But some folks are having really interesting discussions about like what do they want to do. Like I'm surrounded less so about the topics, but like I'm really surrounded by people trying to sort out what to do and like their careers and what to study and how do they do that. And that's a related theme to the Nick Week panel that I'll be doing stuff with later too. So it's just a big nexus around that. I know it's super abridged and brief, and I'll leave it there. But just a lot is happening, and I've kind of been like Rip Van Winkle asleep for 2 weeks, and now it's like, oh yeah, like there's so much happening. So I'm just trying to, you know, catch the moving tide again. Now that I'm more functional. So any questions or comments before we go? I know we're late, but I appreciate this meeting and what we're doing here too.
Oh, thank you. Muted. People are muted. But
Yeah. So yeah, that's a great update. Thank you, Jesse. Yeah, a lot of things going on. Congratulations on the Princeton Envision. Moving to the next step on that and becoming a historian of the meetings and that. That's always a good sign that you've been kind of recognized in that space.
Oh, yeah. Also, thank you for that. And one other thing, for anyone it's limited right now. It's basically a pilot program. But I do encourage folks, if you're a little tied to anyone in Harvard, it's basically Harvard undergraduates, Harvard juniors, the School for Moral Ambition. And they're doing like some big publicity, some with big buses at Harvard, Princeton, and Stanford, I guess now. I just saw today. The School for Moral Ambition is doing these pilot programs to get juniors and underclassmen juniors to basically think about impact with their career